all of these together, here, put all of this together, we get for that first term for gradient E T. Of course, we get our 1 over QC over not. And then there term there. E. And all these nasty derivative terms there, we can put together an expression E plus C squared minus I squared plus times the gradient of T. So we're still left in all of these expressions there with the gradient of TR. So we have to figure out how does the retarded time change with changing our own position here. Well, but again, we know that C T minus TR was R, right? So that means minus C gradient of TR is simply just the gradient of this length R, the gradient of our distance R. We can write that as gradient, the length R is of course the square root of R dot R, right? Good. Gradient of the square root is first of all just the derivative of the square root. So this is 1 over 2 times the square root. And then we have the gradient of R. For that, we can use our nice gradient of dot product again. Only that now the vectors A and B are the same vectors, they both are. So we get twice this term, twice that term. So this is twice, so the 2 will cancel out. Because this factor in front is just 1 over R, right? So we get R dot gradient R plus R cross R, right? Okay. And the book tells you get again in the derivatives here, just with velocities, we take the derivative of R, we take the derivative of the retarded time. Make the long story short, as I said, I don't think it would be very instructive now to go through another 4 or 5 steps here. You'll find for the gradient of TR in the end, we get an implicit expression here. We have gradient TR on one side. All of these gradients here, curls, will involve similar terms as we had here. So the gradient of TR not multiplied with anything else, right? So you'll get gradient of TR on both sides. You can solve that equation then for gradient of TR. What you'll find is that it's minus R over RC minus please take the time to go through the steps in the book. I think that's more instructive than me trying to figure it all out. Right about it. That's that. This we can then put in here for the gradient of the R. So what we'll find is the gradient V minus T comes out to 1 over 4 not C over. So you can see that we get yet another factor. And there's another factor, 1 over RC minus R dot V coming in. So we actually get 3 of these factors here. V to the 3rd power, and then the remaining terms. Well, actually, we have this in here, we have this factor not here, so we have to essentially multiply it back in. And this. Okay, that's not quite the final answer yet, because we still need dA over dt. Again, mostly what we'll get, of course, we get time derivatives, so we get velocity terms for these, and we get time derivatives of v there as well, so we get acceleration terms. Writing this all together, so let's first of all do one simplifying definition here. So we define a vector u that is something like a velocity that has unit vector of r, so the direction, but the speed of light in this direction, minus the physical speed of the particle. So this is a definition that just saves quite a bit of writing, nothing more to it. So this means what we have here is, well, we have r multiplied in here. So our factor rc minus r v, we can just write as r. So that simplifies that here. This is just u to the 3rd power, but this is r u to the 3rd power, this is r. So that's just simplifying the writing. What we find at the end, putting all of these together, we'll have a couple of terms here with the R, A, and B multiplied together. A rule that often comes in if you add all of these terms up is that we have R cross A. This, the AC-CAB rule, right? B AC minus CAB. Right, so that's U R dot A minus A R dot U. That's these kind of terms we'll get in here, and more terms from the T. These we can combine ultimately to get triple cross product like this. What we find in the end as our final result of the field of a moving point charge is then Q over 4 pi. Too much. Power. And then we have 2 terms like that. there's one term that essentially just involves the velocity term here. So the c times the direction in which we're looking minus velocity. And then we have one term here that includes an acceleration. So this is our main final result here. So we have one term that only involves velocities, no accelerations. So this is the term that's typically called the velocity field. And then there's a second term here that involves length, velocities, and the acceleration. So this is then called the acceleration field. And for reasons that will become clear in the second half of the lecture, is that this is also called the radiation field. So we'll motivate that in a couple minutes, that it's only this term from which we get actually radiation from. We'll explain why in a couple minutes. So, again, I encourage you, please go through the entire derivation at home, take your time. It would not make much sense if I try it. This is our electric field. Of course, we want to know the magnetic field as well. So, we want to know field as the curl of A. But we know that A was, that over there, this is simply the particle's velocity over c squared times E, right? That we can write out as, of course, there's 1 over c squared in front of everything. You can write this out as just the potential times the curl of E, right? Plus gradient of the potential we have calculated right there. Curl of V actually we have calculated as well. Right? That gave us something like E cross A cross gradient of TR. We write all of this out to get for the magnetic field an expression that is Q over 4 pi epsilon C R cross product with very similar terms as we have there, c squared minus b squared, and this is E plus and all of the individual terms that are summed up together. We have calculated in these steps, so we don't want to go through that. Okay, now we remember that our vector v u was rc minus v. So, since much of this looks very similar, remembering this triple cross product rule here, the c minus v squared u, only we have v there, and somehow different sign. And here, instead of this cross product here, see we have still v instead of u, and both plus signs don't quite seem to work with that. But since we are multiplying everything with our length vector or distance vector r, and your cross product, of course, what is, if we have r, let's assume we have some kind of r unit vector on the, in this right hand side here. What is that? So if there are any terms in here that have an r unit vector in there, we cross that with r, what comes out? Take the cross vector, the cross product of two parallel vectors. What is that? You seem to agree? What is it? A vector cross product with itself is 0, right? Because it's the sine theta, the angle between the two vectors. If they're parallel, then that angle is 0, right? So that is 0. So that means, in fact, wherever there is v here, you can actually replace that by minus u, right? Because in the end, so if we replace everything, everywhere we have v here, here, we can actually replace that by minus u. And then doing the cross product gives us the exact same result, right? Because there's only the 0 ones in there. So we can write this then as v being p over 4 pi c 1 over cubed cross c squared minus v squared u. That's actually a minus sign, right? Plus, well, then, see, this becomes minus u r dot a plus a r dot u. Well, and this is BAC minus CAB. So BA, there's an A here, cross, so BAC, A cross U, right? Or that is minus R cross A, right? So minus R cross. That now looks an awful lot like the terms we have here, right? C squared minus B squared U and R cross U cross A. Okay. So just with a sign in front of everything. And we have R cross these vector terms. So we can put this together as here there's just a 1 over c in front of it. Otherwise, all the factors in front are the same. And then we have, so this r, of course, we can write as length r times r unit vector, right? That way you also get the R factor here. So the only difference is that we cross all this thing with cross. Again, this is our magnetic field. So that's our second main result. The magnetic field B is almost the same as the electric field, only that we have essentially, so B is R cross E. That means the electric field and magnetic field are always perpendicular to each other. If you have a point source there, that is accelerated in some direction, the electric field goes that way. The magnetic field, you see, will always be perpendicular to E, and always perpendicular to the direction of viewing towards the source. Okay, here we also see in what direction an electric field will point. So let's look at these expressions a little bit and figure out in what directions the fields are pointing. So let us assume that we have a particle that is moving. So we talk about the fields from charges. This is now that's becoming really important if you want to go into radiation, if you want to do astrophysics. This is essentially the fundamental thing with which everything starts in radiation field. Radiation of a particle becomes really only efficient if the particle moves relativistically, so with the speed almost the speed of light. So if there's a very large velocity c almost, or v almost equal to c, then you can see that this first factor typically becoming very small, right? Because c squared minus v squared becomes less. So then the fields are dominated by this term R cross E cross A. So which direction is that function? Let's again say we are looking at direction R, is our charge Q. Let's assume the velocity is going in this direction. And we assume the particle is accelerated in some other direction. So the particle is accelerated, say, in this direction, so towards us. Then where are these funny vectors pointing? So U cross A, so let's say A goes in this direction. Actually, that's not good. Let's say the particle is actually coming out. The acceleration goes out of the. So this means the acceleration, let's assume, comes out of the plane. We go in this direction. Then, well, the vector U is unit vector c. So U goes somewhere in this direction, minus v. So the vector U is somewhere in the plane of the board and goes somewhere minus v